Imagine an environment so extreme that a traditional aircraft would just tear itself to shreds, and with temperatures so high that even a rocket engine couldn't withstand. These are just some of the characteristics that vehicles have to undergo while in the hypersonic regime. Hi, my name is Prem Penkar, and me, along with my fellow classmates Benjamin Landers, Alyssa Landry, Nehemiah Horak, James Kudaferis, and with guidance from our professor, Dr. Garcia, have laid the foundation for a new and improved hypersonic glide vehicle. Now, what exactly are these vehicles? Well, a hypersonic glide vehicle, or HGV for short, are aircraft or vehicles in general capable of reaching extremely high speeds faster than Mach 5. From a military perspective, HGVs are currently subject to an arms race. So, countries such as the US are prioritizing the research and development of HGVs due to their unique characteristics. Specifically, they are very maneuverable and undetectable from enemy systems. Now, our HGV comes into play when looking at hypersonics from a scientific perspective. Currently, data on hypersonic flows is very limited, and the field itself is not fully understood. So, we want to be able to provide data points from our flight tests that can then be fed to other academic and research institutions for post processing and make advancements for the future. So, some of these data points include temperature and pressure data. So, both of these data points from our flights can be used to compare against simulation data, which can then in turn cut costs on testing in the future. Looking at some of our key stakeholders here, so as I just mentioned, the scientific and research community will directly use our data from flights. So NASA and other academic institutions such as Georgia Tech are just a couple, just to name a few. Government agencies will use our HGV for defense purposes and ensuring homeland security. So this includes the Department of Defense and NATO. Also, there are going to be a numerous amount of corporations directly working with our HGV, including launch providers that will directly boost our HGV to the upper atmosphere. Also, we will be working with manufacturers to ensure high precision parts and effective quality control. With that goes, minimizing the risk to the general population. So we will ensure that our vehicle is safe and efficient while operating. Looking at some of the specific needs, of course, we need to be able to go extremely fast at hypersonic speeds, and the total cost has to be less than $3.2 billion. Now, with all of the data points stored on our HGV, that all needs to be transmitted live to ground stations to ensure that the vehicle is functioning correctly throughout the entire phase. Looking at some of the competitors here, so China and Russia have their own versions of HGVs, but the issue is data on these aircraft are really not well known, and Russia has really only confirmed one successful flight test. Additionally, both of these programs have had an extremely long R&D process spanning well over a decade. So we want to be able to cut down on this time and go into production as soon as possible.
Our ConOps outlines our general system operation. It begins with receiving of a launch command and the transportation out to our designated launch site. This takes about 5 minutes. After a 2-minute launch readiness check, our vehicle is launched to the separation height. This takes about 1 minute. This is followed by a 10-minute boost phase, a 15-minute glide phase, and a 5-minute terminal phase. This is reflected in our functional architecture, which is broken down into our launch vehicle, our hypersonic glide vehicle, and our ground station. Our launch vehicle is responsible for delivering our HGV up to the separation height. The HGV is then responsible for collecting the relevant flight data and storing a target. The ground system is responsible for receiving the flight data, decoding this data, and storing the data in our flight database. Our engineering characteristics were identified based on known challenges of the hypersonic flight regime and customer-specific challenges. Existing systems were also investigated to determine feasible target values. The most important engineering characteristic is our flight speed of Mach 5. Other characteristics include our maximum heat flux, system mass, communication data rates, flight profile, and manufacturing precision. Of these characteristics, some customer-driven characteristics include our telemetry data collection and our payload variability. This includes the support for different scientific payload types. Some of the science-related characteristics are derived from existing wind tunnel and CFD data, which is shown in papers. These set a baseline for the type of data that is to be collected during flight. Our customer requirements were collected from all group members. Customer requirements consist of scientific goals, defense and national security goals, and public interest goals. Specific values were derived from existing systems and programs. Scientific requirements revolve around the hypersonic flight regime, different flight profiles, and scientific data and experiments. Defense and national security requirements also revolve around scientific data. Additional requirements include program cost and integration with existing systems. Public interest goals revolve around the safety of the population. In terms of how our engineering characteristics are correlated, many are correlated with our Mach number, but also the payload types and science hardware are highly correlated with the internal temperature of our system. System mass is also negatively correlated with many other design aspects. In terms of importance and customer requirements, we set high importance on our live data transmission, our flight speed, data security, system cost, and heat and vibration resistance, while we set a lower priority on open data, detectability, and open system architecture. In terms of engineering characteristics, we set a high importance on our data, while also setting a high importance on our heat flux. Other systems were considered from both China and Russia. In terms of customer requirements, our system is generally comparable. Design aspects we excel at relate to our data and our reliability. In terms of our engineering characteristics, we once again perform about the same. China's HGV is somewhat lacking in data due to its low number of flights, and both HGVs are heavier than our target value, while our HGV is also more adaptable to US systems and payloads. In terms of technical difficulty, we expect many system aspects to be of high challenge, but of these, the temperature is expected to be the highest. This is because the temperatures experienced during hypersonic flight extend beyond the operating conditions of most structural materials and hardware, but less challenging aspects include data formatting and acquisition.
All right, hey everyone, my name is Benjamin Landers, and today I'm going to take y'all through how we have established value in our project via some digital modeling methods. So to get started here, we've got a snapshot of our model's homepage for our hypersonic glide vehicle project. And this is really a one-stop shop for everything we've done in the project. It's got all of our requirements down to our functional architecture, physical decomposition, all the way to simulations and traceability from each one of those model elements back to those requirements that we've laid out before. We've even got some stuff in here that you might not expect to see, like our team contract and QFD. And really, it's just kind of acting as the team's PLM software in a sense, and authoritative source of truth that we continue to go back to and update throughout the project. All right, and so here we've got a comprehensive list of our requirements that we've made. There's 17 in total, and you can kind of see here it's a little odd to read, but number 3 is actually the top level requirement. That's going to be meeting the HGV mission capabilities, and then that's composed into a number of subsystem and kind of component level requirements for Mach speed, payload requirements, mass roll-up requirements, flight requirements, altitude requirements, things like that. And then here we've got kind of a graphical representation of those same requirements. So you can see here up at the top, we've got our main HGV mission capability, and then that kind of contains these next level of kind of subsystem level requirements for speed, payload capability again, and then data transmission. And then those are again containing another kind of component level for things like our pressure tap data, transmission data, temperature data, and things like that. All right, and so here we've got our physical architecture. We've got our main system at the top for our hypersonic glide vehicle, and this is composed of 7 different subsystems. So we've got our chassis, propulsion, payload, onboard computer, thermal protection system, and transmitter. And then we've got our instrumentation subsystem, which is actually composed of 3 different components, being the thermocouples, pressure taps, and transducers. And we've actually tied multiplicities with each one of these components, and you can read that as there's 0 to 24 thermocouples or 0 to 12 pressure taps in this instantiation of an HGV. All right, and so here we've got an example of how we've been able to automate some of our processes. This is a mass roll-up parametric, and it goes all the way down from the components of our system, and then it takes the masses of those components, rolls them up into the subsystem that holds those components, and then rolls all of the subsystems up into the main system, and we get an entire mass readout for our HGV, and that allows us to see if we're really meeting that mass restriction requirement that we've laid out beforehand. All right, and we have been able to establish some traceability for our project. So here we have a satisfaction matrix, and this just shows the exact model elements that are satisfying each requirement that they are meant to meet there. And here we've got some verification. So we've actually been able to simulate 3 different instantiations of our HGV, and 2 of those simulations have come back with verifying all of the requirements that we've laid out beforehand. And that just shows us that we've been able to meet kind of the standards of what we've set out to build for this HGV. All right, and with that, I will pass it on to talk about generating and evaluating alternatives.
Hello, I'm Melissa, and I'll be explaining the process we use to generate and screen our alternative design options. Here we've created a morphological matrix to explore the entire design space for a hypersonic glide vehicle. What sets our team apart is that we didn't chase ultra-exotic options or hypothetical technologies. Instead, we anchored our selections in what delivers the highest value with the lowest program risk. Each subsystem was evaluated against themes that matter most for a feasible HGV concept: cost, weight, reliability, and manufacturability. While some concepts rely heavily on unproven materials or complex geometries, our configuration is anchored in high TRL, high confidence technologies that can be built and tested now, not years from now. This gives us clear competitive edge. We can execute faster because our materials and subsystems are already producible today. We reduce integration and thermal structural uncertainty, which is one of the biggest risk drivers in hypersonics. We control cost by selecting options with mature supply chains and predictable manufacturing processes. We preserve performance where it matters: aerodynamic efficiency, thermal survivability, and mission reliability without over-engineering the vehicle. The result is a design that is realistic to build, reliable to fly, and achievable within schedule and cost. This balanced architecture positions our concept as the most credible, lowest risk path forward. Before we move into specific risks for the proposed concept, I want to establish the framework we're using to evaluate them. This slide shows the standard risk matrix that we've used to analyze our design. The purpose here is to demonstrate that our team is not only innovating, but doing so within a proven, structured, disciplined risk management process that's aligned with aerospace best practices. We categorize risks as high, medium, or low based on how likely they are to occur and the severity of their impact. The probability scale allows us to evaluate how likely a risk is to materialize, ranging from near certain events to those that are extremely improbable. The consequence scale classifies risks by the magnitude of their impact on the program. The color-coded matrix on the right gives us a clear visual way to prioritize where we should focus our attention. It ensures that when we talk about risks later on in the presentation, we're doing so with a consistent quantitative framework and not in a subjective way. Here we've identified key risks associated with developing and testing the vehicle, along with the mitigation plans already built into our project. I want to draw attention to a few of the highest priority risks in the program. First, program cost carries a relatively high likelihood of exceeding budget, which is common in emerging hypersonic programs. To stay ahead of this, we're conducting recurring cost reviews and maintaining contingency margins. The most critical technical risk is TPS failure. If the material cannot survive hypersonic heating, the vehicle will be lost. To mitigate this, we're performing rigorous, flight-relevant thermal testing prior to launch. Structural loads present another high impact risk. The aerodynamic and thermal environment at hypersonic speeds is extremely demanding, so we have extensive structural load testing planned to ensure survivability at peak conditions. Together, these mitigation strategies demonstrate that we're not just identifying risks, we're actively controlling them to keep the program on schedule, on budget, and aligned with mission success. This slide shows how those risks map onto our risk matrix. The goal here is to provide a clear visual of where the program faces the highest exposure. The red zones highlight the true program killers, the risks that can take down an entire project if they aren't handled correctly. TPS and structural failures sit in that red area at the intersection of high likelihood and catastrophic impact. Their placement reinforces why our test program is so heavily focused on thermal and structural validation. Adjacent to this, we see program costs and software failure. While one is programmatic and the other is technical, both pose high impact threats if unmanaged. The remaining risks fall in the yellow region, with impacts that are manageable given the mitigations already embedded in the project. The key takeaway is that we're not just listing risks, we're strategically prioritizing them and addressing the high impact items early. This level of insight and structure gives our concept a clear competitive edge as we move forward. Now that we have discussed our risks, the natural next question is, which technologies offer the most value and why did we choose the ones that we did? James will take it from here to walk through the alternative technologies and the accompanying trade study analysis.
Hi everyone, I'm James Kudaferis. I'm going to be continuing on our evaluating alternatives section. So we're going to start with our trade study, which was on the glide body shape for the hypersonic glide vehicle. Our criteria we evaluated were lift over drag, longitudinal stability, roll stability, and aerodynamic heating. The alternatives we evaluated were a blended body, wave rider, delta wing, and a blended wing. As you can see, aerodynamic heating had the highest weight. This is because for a hypersonic vehicle, the thermal loads are very high, so this is going to be a main design driver. For longitudinal stability, that is the lowest weight, and that is because we have control surfaces which would be able to correct for any longitudinal deficits we have. The blended body was the geometry which won this trade study, and that is because it can balance the thermal loads as well as a high lift over drag. However, this was not the only trade study we did, as we also did one for structure, thermal protection system, communication system, navigation and control, cooling, launch, and power source. So this was just a glimpse into the trade studies we did, but we actually did them on multiple subsystems. Continuing on to the verification and validation section, you would have seen these requirements earlier. I'm just going to go through the ways that we are going to verify them. For mission capability, requirement 1.1, we're going to verify this by using a trajectory simulation, which uses an aerodynamic database, which is generated from CFD and wind tunnel analysis. This will be done by the aerodynamics and flight dynamics team. For requirement 1.2, we're going to need to make sure that our vehicle is compatible with two different payload types. This will be the responsibility of the Department of Energy to ensure that their hardware is compatible with our software. Requirement 1.3 will also be done using the trajectory simulation, as it will be able to track the time of flight. So this will be the aerodynamics and flight dynamics team as well. Requirement 1.4 will be done using a CFD validation and wind tunnel testing to ensure that within the altitude range prescribed, we are able to have enough command to do our maneuvers. Once again, this will be the aerodynamics and flight dynamics team. Requirement 1.5 can be done using CAD modeling by prescribing density values to each component. And then we will also weigh the vehicle pre-flight to ensure that it meets the weight requirement. This will be handled by the mass properties team. Requirement 1.6 will be verified using a ground test and thermal simulations to ensure that our internal temperatures are within our safe limits. This will be done by the thermal team and is critical to ensure that our internals remain intact. Requirement 1.7 will be handled by the radio frequency team, and this will ensure that we have communication between our antenna and receiver, and this will be done using a ground test. To conclude, we want to reiterate that our hypersonic glide vehicle will be providing very crucial flight data to the scientific community. The proposed vehicle was created by considering engineering and customer needs and then creating requirements. Multiple subsystems were considered based on these engineering requirements in it, and they were evaluated within trade studies to ensure their feasibility in a prototype. Mission risks have been identified and verification processes were established to ensure that our risks are mitigated. The vehicle meets all these requirements and engineering characteristics and would be a great source of information for the scientific community. As you've seen within this presentation, a lot of the work has been done, so we'd be able to hit the ground running if we were to get funding to support this project.